Thank you, Ravi, and thanks to Claudio for the invitation to participate. Here are the disclosures. So to cut to the chase, this is the fundamental element of a filter that's used for CRRT, and that's the hollow fiber membrane. So essentially, somewhere between 7,500 and 15,000 of these hollow fibers, depending on the filter surface area, are gathered together in a so-called bundle, put inside a plastic casing, and you have a filter. So that's essentially what we're going to be talking about for the next 30 minutes and some of the underlying principles behind that process. Obviously a very complex process that I've just very significantly simplified. As there will be some aspects of this presentation that overlap and maybe extend what Dr. Ronco mentioned. He, in large part, although in the past this may have not been the case, for the most part these days we're just leveraging membranes that are produced primarily for a chronic application. We're applying those in the acute world. That didn't used to be the case necessarily because of the conditions that were used, and I'll talk briefly about that. For the most part, though, we're leveraging what goes on in terms of chronic filter and membrane production. And there are a whole host of different membrane structures. For the most part, of course, we're using high permeability synthetic membranes for CRRT. The vast majority of them have a so-called asymmetric structure, as Dr. Ronco mentioned, where in the inner part of the fiber that actually contacts blood, there's a thin layer, the so-called skin, which really determines what molecules are removed and what molecules stay in the blood. And then the rest of the membrane thickness is essentially a support structure, which may come in the form of more looking like a sponge or more looking like finger projections. But essentially, that layer of the membrane not only provides support, but also provides surface area for absorptive removal of some molecules, which we'll talk about. Now, traditionally in the past, at least in the nephrology domain, we've tended to classify membranes according to material. This is the basic structure, or basic classification that has been historically used, modified cellulosic versus synthetic membranes. I don't even mention unmodified cellulosic or so-called Cooper-Fein membranes because they're essentially non-existent now, especially in CRRT. So these are the basic options, and again, for the most part in CRRT, we're dealing with high flux synthetic membranes. There are some differences between, for instance, the wall thickness of a cellulosic membrane versus a synthetic membrane. That really has more relevance in the chronic setting where diffusive transport, as Dr. Ronco mentioned, is highly dependent on membrane thickness. As we'll talk about, that's not such a major consideration for diffusive solute clearance in CRRT. Now, a few slides now is how do we actually characterize a membrane and a filter? One aspect is the ultrafiltration properties. And as Dr. Ronco mentioned, essentially the so-called ultrafiltration coefficient, or KUF, is the slope of the line, the regression line between ultrafiltration rate and transmembrane pressure. Now, typically, there are specified conditions under which a KUF is generated. Specifically, typically, blood is used as the fluid at a certain hematocrit because, as we'll discuss, red blood cell concentration and particularly protein concentration can influence the hydraulic permeability of the membrane. So there are differences between lower flux and higher flux membranes. That's manifested as either lower or higher slopes. And again, as we'll talk about, you see this bending of the curve, if you will, that represents secondary membrane formation. Dr. Ronco referred to this as concentration polarization, but essentially it's an additional resistance to both fluid and solute transport. And again, we'll talk about that extensively as we go on here. Another mechanism or approach to characterizing a membrane is to describe the sieving characteristics. So this applies when a membrane or filter is used in the convective mode or in an ultrafiltration mode. And the sieving coefficient is defined as the concentration of a solute in the filtrate divided by the concentration of that solute in the plasma based on a simultaneous measurement. Now, the sieving coefficient is equal to the inverse or 1 minus the rejection coefficient. They're intimately related, and as we'll talk about, the secondary membrane can have a significant effect on these parameters, as of course the basic sieving properties are of course a function of the membrane permeability in the first place. The general idea here is at a molecular weight of about 10,000, between 10,000 and 100,000 of course lies the molecular weight of albumin. So typically or historically, high flux membranes used in high flux hemodialysis for in the chronic setting, the profile stops or cuts off, if you will, just before the molecular weight of albumin, at least after the filter has been exposed to blood or protein. When we talk about high cutoff filters, it's a totally different dynamic in terms of kind of playing around the molecular weight of albumin to maximize the removal of larger solutes up to the point of albumin. Again, we'll talk about that further. This is, in essence, what happens with secondary membrane formation. So after the filter, the membrane's been exposed to blood, or at least a solution that contains proteins, there's an instantaneous absorption of proteins in a non-discriminating way to the membrane surface. And essentially, that reduces the pore area through which both solute and water transport can occur. So for instance, if you look at a test solute, these are so-called dextrans. If you first look at a membrane that's only been pre-exposed to saline, and then you measure the rejection coefficient, remember sieving coefficient 1 minus rejection coefficient, the rejection coefficient basically is 0 for a 5,000 Dalton test solute, whereas a membrane that's been exposed to plasma, protein-containing solution, that rejection extent is about 70%. So a substantial impact, and the impact relatively increases as a function of molecular weight, solute molecular weight, in a direct way. Now, taking those things together, water permeability or hydraulic permeability and sieving properties, there have been a series of proposals on the way that filters should be characterized. Again, in the old days, we used relatively simplistic classification schemes. We focused way too much on membrane material. We then focused way too much on just the water permeability. So these newer classification methods are combining water permeability or hydraulic permeability, that is KUF, along with solute permeability or sieving properties. And this is just an example of a proposal for combining water permeability with, for instance, sieving coefficient for two important molecules, beta-2 microglobulin and albumin. Now, you'll notice that these water permeabilities are very high. You'll remember that I mentioned before that typically KUFs that are reported, for instance, when you open up a box of filters and you read the direction insert, the KUF that's provided is based on when blood is used as the filtration fluid. So in other words, it takes into account secondary membrane effects and so on. These are, if you will, pure water permeabilities, virgin membranes that haven't been exposed to proteins, and that's why you see these numbers are so much higher than what you typically see for clinical KUF. Another proposal that's been made is to, and Dr. Ronco alluded to this, another proposal that's been made is to classify membranes and filters according to not only the molecular weight cutoff, which has been kind of a classic parameter, which is defined as the point on the sieving profile at which the sieving coefficient at a particular molecular weight at which the sieving coefficient reaches 0.9. That's been the classical parameter. Now, the newly proposed parameter is the so-called molecular weight retention onset. So as the name implies, it's early on in the course of the sieving profile at what molecular weight the sieving coefficient or corresponding sieving coefficient is 0.1. So the idea of modern membrane production is to produce a relatively narrow width between the molecular weight retention onset point and the molecular weight cutoff. In other words, a steep sieving profile is generally what is desired from a membrane manufacturing perspective. Now, if we look at what actually happens when blood flows through a hollow fiber membrane, so if you think of it in terms of engineering principles, it's the same as blood flowing through a cylinder. And there's literally hundreds of years worth of work of fluid flow through cylinders. So that information can be applied to hollow fiber membranes. And we'll talk in the next slide what exactly is meant by laminar flow and a so-called Newtonian fluid. I know Dr. Ronco mentioned that in some respects blood is a non-Newtonian fluid, but for the most part, the parameters that are used, particularly in CRRT, generally result in blood being a so-called Newtonian fluid. And again, we'll talk about that in the next slide. But basically, the fundamental relationship for blood, when it behaves according to laminar flow and behaving as a Newtonian fluid, is that the blood flow rate is a function of the so-called end-to-end pressure drop. In other words, there are arterial to venous end pressure drop divided by the resistance to flow. Very basic concept. And in fact, if you break down the denominator of that equation and you just isolate out the resistance you can see is a direct function of fluid viscosity. So that's determined by blood viscosity, which to a large extent is determined by hematocrit, and also the length of the fiber. On the other hand, it's inversely proportional to the radius of the fiber. And in fact, it's the radius of the fiber to the fourth power. So a relatively small decrease in the inner diameter of the fiber can have a significant impact on the resistance to flow through the fiber. So what that practically means is that if you're trying to achieve a certain blood flow rate through a catheter, and the filter that you're using has a membrane that has a certain inner diameter, and you, for whatever reason, decide to change to another filter that has a membrane with a smaller inner diameter, to get that same blood flow rate through that new filter, then a higher pressure drop has to be applied, everything else the same being considered. Now, if we look further into what's actually going on inside an individual hollow fiber, again, we're talking about blood as a Newtonian fluid and also laminar flow. So first of all, laminar flow simply means that blood flows according to, if you will, streamlines through the cylinder or through the hollow fiber. Now that's opposed to turbulent flow, where there's vortexes and eddy flow, which disturbs that nice smooth laminar flow, which occurs for the most part in traditional dialysis therapies. Now, what happens here is, I think as Dr. Ronco alluded to, you have blood entering the hollow fiber in so-called plug flow, which means that if you took a cross-section right before the filter, the velocity would be the same entirely through that cross-section. But once the blood enters the hollow fiber, it develops a parabolic flow profile, and the maximum blood flow within the hollow fiber is exactly in the middle of the hollow fiber. And the velocity is the lowest, in fact, is 0 at the wall because of the viscous nature of blood or the fluid that's flowing through the hollow fiber. So there's a so-called viscous drag effect, which results in this parabolic velocity profile, which as you move away from the center of the hollow fiber, the velocity gradually decreases again to reach a point of 0 at the wall. So the shear rate that Dr. Ronco mentioned is basically the velocity gradient. It's the steepness of this parabolic flow profile and how quickly it declines away from the center of the hollow fiber. And it behooves the prescriber in CRRT or any dialysis therapy to understand this, because the higher the shear rate, in other words, the higher the velocity gradient at the membrane surface, at the interface between the blood and the hollow fiber membrane, the greater that velocity gradient or shear rate, the more that secondary membrane effect is going to be attenuated or dissipated, and theoretically at least, greater preservation of membrane function will be attained. And if you look at just some of the equations based on, again, the fundamental assumptions of Newtonian flow of a laminar fluid, you can estimate the velocity gradient, in other words, the shear rate at the membrane surface, to be 4 times the average velocity divided by the radius of the hollow fiber. So this takes into account the basic considerations that of what's actually going on within the hollow fiber. And of course, velocity is directly related to blood pump speed and blood pump through the membrane, through the hollow fibers, and the radius of the hollow fiber membrane is certainly at the discretion of the prescriber of the therapy. Now, moving on to, again, emphasizing this idea of the effect of secondary membrane formation and how that relates to shear effects. So higher blood flow rates result in dissipation of secondary membrane effects, as I mentioned, because of the velocity gradient effects or shear effects. So you have one condition established with a relatively high sieving coefficient, or the inverse, a relatively low rejection coefficient. At lower, more, if you will, sluggish blood flow rates, allows for greater accumulation of proteins at the membrane surface because of lower shear rates. That generally will translate into lower solute sieving coefficients and conversely higher rejection coefficients. Now, if we look at the situation in conventional hemodialysis, the goal in conventional hemodialysis, because of the relatively short duration of the therapy, is to maximize the diffusive conditions for solute removal, for clearance, particularly small solutes like urea and creatinine. And generally speaking, that can be visualized as a stepwise process where there's a resistance to flow, resistance to mass transfer in the blood compartment, the membrane, and the dialysate compartment. And then within both the blood compartment and the dialysate compartment, those can be demarcated into so-called bulk flow and boundary layer flow. Now, the boundary layer is an effect of the viscous drag forces that I mentioned before. And if you want to conceptualize the mass transfer resistance, it almost entirely resides in that boundary layer, at least on a mathematical or conceptual basis. And the same can be said for the boundary layer in the dialysate compartment. So the basic reason why we try to use as high of flow rates as possible in chronic hemodialysis or conventional hemodialysis is to dissipate these effects to decrease mass transfer resistances in both the blood and dialysate compartment, and to make sure in general that those are not the if you will, rate limiting steps in the overall mass transfer, at least of solutes like urea and creatinine. Now, if we look at, again, as I mentioned before, largely what we're doing these days in CRRT is borrowing from fibers and filters that are manufactured for ESRD patients. That's generally the case. Now, that didn't used to be the case when, for instance, arteriovenous therapies were performed. Obviously, when there's no blood pump involved and blood flow through the filter is dependent on the patient's mean arterial pressure, the end-to-end pressure drops and the intra-filter pressures were much lower. And therefore, a driving force for those therapies was to minimize the resistance of the filter at any cost. So what that meant was, going back to the equation that I showed before, developing filters with relatively large lumen, large inner diameter lumens, and also filters that had relatively short fiber lengths. Again, with blood pumps now universally part of CRRT systems, those considerations have fallen by the wayside. And that just is demonstrated here, where a membrane that's made more or less of the same material. You see in the chronic setting here, there are some differences in terms of inner diameter and small differences in the effective fiber length. But generally speaking, those differences are not huge. And you'll see that the membrane surface area is largely a function of the number of fibers that are in the fiber bundle within the casing of the filter. So in these two filters, really designed for chronic use, there's somewhere between about 13,000 and 15,000 hollow fiber filters, whereas in these lower surface area filters, somewhere between 7,500 and 10,000 filters. So that's by far and away the largest parameter driving membrane surface area. And in fact, in CRRT therapies, and if we specifically focus on diffusive therapies, CVVHD, it's a completely different mindset compared to the considerations that we talked about for chronic hemodialysis and minimizing diffusive mass transfer resistances. In CVVHD, this is an older slide, and we'll talk about newer considerations here in a second. But essentially, I think as Professor Ronco alluded to, the idea is not necessarily to absolutely minimize mass transfer resistances, is to make sure that for whatever dialysate flow rate is being used, it's saturated with respect to at least small solutes and even larger solutes that's desirable. So what that means is the incoming blood concentration of the filter is essentially the same as the effluent concentration of that same solute. So that's the idea in CVVHD. And as higher blood flow rates, there's been an interest in using higher blood flow rates to provide higher doses. There's been a movement away from relatively low surface area filters, this older study about a 1 square meter filter, to abide by or to tolerate or accommodate the higher blood flow rates that are being used these days. There needs to be, for one thing, higher surface area filters, but also different combinations of blood and dialysate flow rate to make sure that, again, solute transfer, saturation of the effluent dialysate is preserved to the greatest extent. And this is just shown here with different filters of different surface area. If you look at the effluent flow rate and as membrane surface area increases, as you look at the effluent dialysate flow rate and you compare that to solute clearances, kind of incremental increases in blood and dialysate flow rate are what really allow that saturation phenomenon to occur. So there have been certainly developments over the last decade or so moving toward higher blood flow rates, higher dialysate flow rates, and higher membrane surface areas. And this slide captures some of those considerations, or what should be considerations in the prescription of the therapy. So let's shift gears a little bit and talk about large solutes for the last few minutes. There's remains very keen interest in extending the spectrum of molecules that are removed by CRRT and not limiting the discussion to the traditional small solutes, urea, creatinine, and even relatively small proteins like beta-2 microglobulin. So this is just an incomplete list of some of the relevant or potentially relevant larger molecular weight solutes that may play a role in patients, particularly critically ill patients with sepsis. And as you can see, these molecules range from molecular weight. There's quite a large molecular weight spectrum and far beyond, orders of magnitude in molecular weight beyond, again, the traditional molecules that we talk about in conventional hemodialysis. So how is the removal of these molecules approached? Dr. Ronco alluded to both of these phenomena. I'll briefly discuss it again. Absorption is one approach, which really is not a relevant consideration for small water-soluble compounds like urea and creatinine, but by a host of different mechanisms, including hydrophobic interactions, so-called van der Waal or dipole interactions, and finally ion exchange mechanisms. All of those phenomena may contribute to the absorptive removal of a particular, let's say, protein or peptide, which may have regions within it that are amenable to absorption by all three of these mechanisms. So one membrane, one filter that's been developed to specifically capture absorptive capabilities or to try to maximize absorptive clearance of not only the typical targets like inflammatory mediators, but also compounds like endotoxin is the Oxyrus membrane shown here. Another approach consists of a more traditional transmembrane removal, but kind of, if you will, tweaking the process a little bit. So the standard technique of CVVH can be used using a relatively standard pore size filter, and that means driving more solute across the filter by using relatively high ultrafiltration and replacement fluid rates. Another approach is to use CVVHD with a standard pore size, since generally speaking, larger molecules tend not to be removed very well by diffusion with these standard pore size filters. There then becomes a rationale for combining a diffusion-based therapy like CVVHD and also increasing the pore size. And that combination may enhance the removal of these larger molecular weight targets. I think Dr. Ronco showed this slide, again, capturing some of these concepts where the sieving profiles, particularly of these newer membranes, high cutoff or super high flux membranes, are just kind of dancing around the molecular weight of albumin depending on protein absorption and secondary membrane phenomenon. That really dictates to what extent albumin is going to be removed. And this shows that in the generation of these kind of membranes and the pore size distributions, all membranes have a distribution of pore sizes. They're not perfectly ideal with one pore size. The distribution in some cases may be a little bit broader with these high cutoff filters versus a standard filter. But again, a lot of it comes down to the interplay between the sieving profile or the pore size distribution and the molecular weight of albumin. If we look at one particular study that looked at two types of polysulfone filters, one standard pore polysulfone filter, and this is used in the CVVHD mode, that's shown here, and a larger pore filter shown here. Comparison of sieving coefficients for a variety of different inflammatory mediators ranging in size between about 10,000 Daltons and all the way up to 52,000 Daltons or 51,000 Daltons, which TNF is when it circulates as a trimer. So these are plasma-based experiments taking into account the secondary membrane effects that we've been talking about. So you see this significant impact on sieving coefficients relative to a standard pore filter, and the effects are particularly pronounced for, or relatively speaking, for the larger molecular weight compounds. And again, you see these differences that play out in terms of clearance, in vitro clearances, more or less mimicking what was shown for the sieving profiles. So there is a way to enhance the removal of these molecules using a combination or different types of techniques: hemofiltration, large pore hemodialysis, and absorptive approaches. So to summarize then, Mr. Chairman, while CRRT membranes and filters have many similarities with those used for conventional hemodialysis, some, I would say nowadays, nuanced differences may exist. but really the differences apply to how they're being used and the operating conditions, flow rates, and so on in which they're being used. As I mentioned, there's clearly been a trend over the past 10 years or so to use higher surface area filters, which really mandate higher flow rates, blood flow rates, and other therapeutic fluid rates to maximize filter function. And then finally, we continue to be very interested in the removal of larger molecular weight, especially inflammatory mediators. And these new approaches are shedding more light on how we might be successful with that. So thank you very much.